continuing the previous part, I will start the cosmological school, part 3, implications. Because originally this was a 5 hours lecture, so I will skip something and I'll explain best at some moment. The topic will start with the implication, and I will turn to the primordial fluctuation of primordial perturbation, which is produced by the implication. So why implication is necessary? We observe the CMB, the cosmic microwave backgrounds after the photon last scattering when the universe becomes transparent by the recombination, so that the electrons, pre-electrons is bounded in the atom. And if we observe the CMB, this becomes homogeneous and isotropic. And this follows a perfect black body spectrum because the photon and the electrons are in the thermal equilibrium. And this spectrum in the 400 sigma alpha, which means that this is a very precise measurement. And because the CMB shows that the very homogeneous and isotropic temperatures, and we need to evaluate that such a temperature's correlation between the different 2 points is possible in the point of the causality. So before that, we should introduce the new concepts, the conformal time. In the matrix with the scale factors which represent the expansion of the universe, there's a moving coordinate which is xc. This is imbalance over the time, even though there is a universe expansion, and the physical distance can be obtained by the multiplication with the scale factor I. And by time derivatives, we can obtain the Hubble's law by inserting the equation number 1. And we can define the conformal time to make the metric as a symmetric for the temporal part and the spatial part. The scale factors becomes a common one if we define the conformal time d tau as dt over the a. It meaning that the for the null-like or light, the matrix, the space-time interval dr squares vanishes, which means that the d tau and the dr are the same. That means that this is the radial directions. So conformal time measures the moving distance of the light. The scale factors are omitted here, so that these drs mean that the moving distance correspond to the coordinate one, not the physical one. So the conformal time measures the moving distance of the light without the expansion effect. So for example, we can calculate the conformal time in terms of the scale factors of the specific moment. We assume that the matter dominant here. By the change of the variable, we can change it from the time to the scale factors, and by using the definition of the Hubble, and we can insert the Hubble's is proportional to the a to the minus 3 for the matter dominant by using the Boltzmann equation. And by integration through the scale factor a, the conformal time is proportional to the a to the 1/2. So by using this fact, we can calculate the how much the conformal time compares with the CMB and the presence time. Because the conformal time tau is proportional to a to the 1/2, and the lattice shift is the inverse of the scale factor. So this means that the tau is proportional to the just to the minus 1 over the 2, where just to the last shift here, and the last shift for the CMB is known as the 100, and then the last shift and the present times. It means that the the ratio between the conformal time at the CMB and the present time is the 1 over the root of the 1700, and this is around 0.03. So the results, the co-moving distance of the at the CMB is the 0.03 of the co-moving distance at the present time. We can do this in the space-time diagram. So this is the conformal time or co-moving distance at presence, and this is the CMB. So this is latitude with the 0.03. And this means that at the CMB there are no causal disconnected behavior shown. So if we compare the CMB size, the physical size, and the causally connected size, which means that this is correspond to the horizon size. And a lot assume that this physical size and the horizon size are same at the present time. So let's notice as a physical size as a lambda, and the horizon size as the inverse of the Hubble. This is for the present time, and we can evaluate the physical size at the CMB time and the horizon size and the CMB time. But evolutions of the physical size lambda and the evolution of the horizon size or Hubble inverse is different. So for the physical size, it proportional to the wavelengths are proportional to the scale factors, and it decreases at the inverse of the temperature. But the case of the horizon size, the Hubble inverse is proportional to the t to the minus 3 over 2. It's because the so if we calculate the so why the Hubble, here. So for the meta-dominant case, from the Boris-Friedman equations, the Hubble scale is proportional to the energy density of the matrix, and it indicates a to the minus 3, so it follows t to the 3, so Hubble follows to the t to the 3 over 2. So the Hubble inverse, the horizon size follows t to the minus 3 over 2, so along the meta-dominant regions. So if we calculate the Hubble inverse at the CMB and the horizon side at the CMB, and by considering the cubic of this value to consider the volume, then the horizon volume is 10 to the minus 4 of the physical volume, which means that there should be the 10 to the 4 number of the patches should have the same temperatures to reproduce the same temperatures in the CMB. This can be drawn as a following diagram. At the present time, the horizon size and physical time is the same, but the CMB time, because horizon size decreased too fast compared with the physical size, so at the CMB moments, the horizon size patches is smaller compared with the physical size patches. So this is called the horizon problem. This means that this is the point. The two small horizon size compared to the physical size of the CMB formation is a problem. So and also not only the same temperature, we can consider the CMB temperature anisotropy and its correlations with the two different points. The delta t of the t has the order of the 10 to the minus 5, and we can measure the different 2 points with the cell measurement with a specific angle with the 1 degree. And because this is just a statistical thing, so we can select the two different points fully. So the important quantity is the mean value, but just the average of the temperature anisotropy is 0 because of the statistically random. So the information is in the 2-point correlation function between the temperature and isotropy, and because we measure these temperatures things over the spherical coordinate, so that this can be expanded by the spherical harmonics via lambda. And the coefficients includes information usually defines as a CL with the factor of the one of the 2R plus 1. And the index L represents the number of the chords. So this represent the monopole, dipole, and the quadrupole for each value of the L, and the number of the M represents the cutting numbers with the vertical directions. So we can plot the coefficient CL over the L from the 1 to the 1000s, and for the small L, this means that there are count numbers of few, so that this correspond to the large regions with large angles between the two difference points. And then for the such large regions, the correlations we can find that the CL is the correlation is the positive, so that this is not random. So these two different points, even though they cover the large number, these 2 points are causally connected. So the problem is the small fluctuations such as temperature and entropy should be also the causally connected. So here's a plot. The physical size is again it's proportional to the t to the minus the 1, so the a to the 1. The origin size is proportional to the t to the derivative minus derivative, so a to the derivative. So the origin size expands more fast. So it needs that the origin side should be the expanded more slower than the physical size. This can be realized by the implementations in the extremely early universe. So the light year between the physical size and the Hubble, the horizon size, can be represented again. This is the definition of the Hubble. So that the light year between the physical size and the horizon size is just a dot. And because in the standard case, such a ratios decrease because the Hubble radius, the horizon size expanded more fastest, so the ratios decreases. This means that the 2 dots of the A's is negative. So standard case, like as a matter of the radiation dominant case, it is make the decelerate expansion. It is obvious because mass makes expansion slowly, but when is the ratio increases, this makes the accelerate expansion. The horizon size should be the largest in the early universe, so that the different two regions can be the causally connected. So under such accelerate expansion can be written as other equivalent conditions with the material by considering the first and second Friedmann equation, especially for the second one, the equivalent condition of the accelerate expansion of the universe is same with the negative approaches. And the second Friedmann equation can be written as the other form minus h dot plus h squares, and this should be positive, so that we can define the new parameter epsilon. This is called the low roll parameters. Also, this is like this with in Platons. We will introduce this later. And also, as a remarks, if we consider the complement time, there is a minus term. If there's accelerate expansion, and the second term is small, so the complement time becomes extended with the negative regions. So in the space-time diagram, there's a negative regions of the complement time, and so that the two difference point at the CMB can be causally connected. And in the diagram of the comparison between the horizon size and physical size, during the implantation, horizon size is just constant. Hubble term is just constant. So Hubble inverse is also constant, but the physical size is still decreasing. So the physical side can get inside the horizon side so that the different point can be causally connected. So the how much the impulations that we now studied. We can define the number of the equal n as the integration of the Hubble over the time. This is just a logarithm of the scale factors with the binary point and initial point. And the result is we now studied the n to the 60. It means that the scale ratio between the scale factor of the binary and the initial time is the e to the 6 t. This is around the 10 to the 26. So this is calculation how the 60 e-board can be obtained. We need the physical size at the impulsion, physical size at the impulsion should be the smaller than the horizon size at the impulsion. This is the condition. Under the physical size can be replaced by the following step. Because the physical size at the present time and the horizon size at the present time are same. And from there, because the physical size is proportional to the scale factor, so we can just multiply the ratio from the physical size. The physical size at an impulsion can be obtained by the physical size times this ratio, and this can be decomposed as such a factors, and this is the same with the inverse of the H0 at the present time, and by definitions this corresponds to the e to the minus n, start of the impulsion and end of the impulsion. And so the equations becomes the H0 inverse AF over H0 e to the minus n should be the smaller than the HI at the impulsion inverse, and the scale factors are proportional to the modulus, so this gives this term. And by replacing the term n is larger than this, we know that the temperatures at the present time on the Hubble at the present time, and the TF and HI we can input some values, and the n becomes a scale of the 60. So that this is the condition for the impulsion, and such impulsion can be realized by introducing the Scalar bill. Always keeps this part very fast. The negative process can be realized by introducing the cosmological constants in the Einstein field equation. This gives the accelerated expansion, but the problem is the impulsion is eternal, not endless in this case. So usually the Scalar field in Platons are introduces. The action can be written like that, and the stress and tensor can be sort of studied, and this is another density in the process. And if the kinetic term is small and the potential energy dominance is, then the relation between the energy and the pressure becomes rho equals minus p, which is correspond to the accelerated expansion condition, and equation of the motion from the action can be obtained like that, so by calculating the Euler Lagrangian equations. Under the slower condition can be the just calculated by the shape of the potential. So the shape of the potential determines all the thing, And if the slow conditions are break, then impulsions and this and impulsions decay to the other particle, which is called the lating. So the importance in the potentials, so we determine the impulsion model, and we can calculate the various quantity, and there is some additional imposed conditions, and we can test such impulsion model. And some things are observationally quite testable. And for the dominant potential terms, the equation motions are just written like that, and this is just a slow law. And the epsilon, the slow law parameters, can be represented by just the potential. So the potential shape determines the slow law parameters. Like we discussed such things in the previous many video. And the number of the epoch n also can be determined by the shape of the potential. So if we consider the power law potential with some specific mass scale, we can calculate one impulsions and this impulsion is as it is happens when the epsilon is equal to the one the law of conditions are broken. So the impulsion field values at the binary moment is the some of the number times of the Planck mass. So this is the super Planckian field, and the n equal to the 60, such as 60 board is condition. So we can also calculate the initial field values of the impulsion. Now I will turn to some cosmological perturbation from the impulsion. To make the structure, so we need the initial small upper density, and this upper density grows by the gravitational instability. Such a cosmological perturbation can be obtained by the metric perturbation and matter perturbation, and in this case, an impulsion is color field perturb. So here is a metric perturbation, one alone. The other scalar quantity, vector quantity, and tensor quantity. Also gives here the variables also. And we can decompose each vectors and the tensor quantity as other scalars and the vector tensor. And this is the degree of freedom. The scalar for scalar, the 4 degree of freedom, and for the vectors, because there are transverse conditions, reduces the 1 degree freedom for each quantity, so the vectors show that the both freedoms. And for the tensor one, the transverse condition which reduces 3, and the twice last condition which is reduced to -1. So the tensor has a 2 degree freedom which corresponds to the gravitational waves, and the summation through the degree freedom becomes a 10, which is correspond to the metric tensor zero with the symmetric conditions. And also for the stress tensor, we can obtain the perturbing one from the Platon's color field. And by the gauge transformations or the gauge choice, this comes from the coordinate independence of properties of the gravitation, the general relativity of the gravities, and we can remove some degree freedom in the perturbations of the matrix. So there's a gauge choice freedom, blah blah something. I always keeps, and we can find the gauge invariant one, but the tensor perturbation is gauge invariant quantity. This is an it is not changes under the gauge transformation, and we can also make the gauge invariant quantity by the combinations of the vector perturbation. And for the color one, some of the shear term, this transforms with only additional temporal part. This is same with the timely parameterizations of the general relativity theory. So there are some several choices. So we can fix the gauges so that we can remove some quantity, or we can only consider gauge invariant quantity. One non-gauge invariant quantity just color curvature perturbations clearly are the combinations of the such delta pi. So we can obtain the equation of the motion of some specific perturbation. This is case of the tensor one. Starting from the action, this is the not standard one. We can obtain the tensor part. We need the second order because we will derivatives for the all around equation. So to obtain the linear one, the second order is necessary, and this is the result of the tensor perturbation equation of motion, which is just harmonic lighter form. Another this is not that this means the conformal derivatives for the time. So the yeah. So keeps going on. The point is the inflation can make the perturbation, but the Bakh's perturbations actually die. The invariant quantity is the combination of the Bakht perturbation again then under this equation, but then the solutions exponentially decreases. So Bakht perturbations are usually neglected, and if we consider the action, this is not standard. There's no time dependence term, time derivative term, so this can be considered accelerated through the whole just a constraint. And if we insert and replace the other field, and the Lagrangian becomes just zero, so the Bakht perturbation are not physical. So the point is the Bakh's perturbation can be removed. So the only remaining thing is the tensor perturbation and scalar perturbation, and the tensor perturbation and the gauge invariant, and already we obtain the equation of motions, and this correspond to the gravitational waves. The remaining one is scalar perturbation, and there are several choices. The one choice is Newtonian gauges. There are 5 scalar perturbations from the matrix B, E, A minus E, and the scalar perturbation from the inflaton delta pi. And in the Newtonian gauge, B and E vanishes, and A and the C is has a precise sign by denoting the pi. Because A plus E is equal to zeros from the last condition when the B and E is equal to zeros. Then the matrix, perturbing matrix is just given by such a boom. There is only the pi, scalar perturbing, and the shear terms of vanishes. B and E is the shear term, and this corresponds to the weak gravity limit. And we can obtain the equation of motions under these gauges, zero components and y component, ij components, and for the matrix and the matrix perturbation, and we can obtain the equation of the motions for the scalar curvature perturbation, which is the gauge invariant quantity. And the otherwise common gauges, E vanishes, delta phi vanishes, and there are A, B, C as a eliminate. C can be just this can be practiced as scalar curvature perturbation, and there are already the 3 equations of motion, and similarly we can obtain the same equation for the R, curly R. This is because the curly R is just a gauge invariant quantity, and this is not standard. We start from the action by considering second order, and we can obtain the linear order for the equation of the motions similarly. So now we need the point is inflaton field makes the scalar curvature perturbation, and this will make some power spectrum depending on the K mode, and it will make eventually the scalar perturbation by considering the additional evolution. This can be written by transfer function. So the first one is how can parameterize these power spectrums and considering the evaluations of the transfer function so that we can obtain the power spectrum. And the second one is actually the such primordial perturbations that can be formalized by the quantum mechanics. So we need the operators for the contingencies and the defining of the vacuum for the such scalar perturbation. But the point is that there is the operator is time dependent and the vacuum state is also time dependent because Hamiltonian is time dependent due to the expansion impact of the gravity. So we will consider this briefly now. So start from the action for the scalar perturbation, and by the changes of the variable u and the z, this is called the blah blah sum of the name of the variable, and we can obtain the equation of the motion, and we can replace it by the simple actions as a harmonic oscillator form, and because this is harmonic oscillator form, we can quantize as a build form with operators and this such by the canonical conjugate relation, and we can expand this with the ladder operator. Now we can define the vacuum. This is the same process as the quantum field or the quantum mechanics. And but the problem is in this harmonic oscillator equation form, the mass, effective mass is delta of the time due to the time dependent Hamiltonian from the expansions of the universe. This makes the becomes the time dependent. So in the equation of the motion, the frequency depends on the time, and this equation just double prime over the jet can be expanded with the a square, h square, and the sum of the dependence of the slower parameter epsilon and eta. So when the such AH is smaller than the K, then this becomes time independence, and this corresponds to the sub-horizon regions. The inequality can be written like this form, and the H inverse corresponds to the Hubble radius, the horizon size, and the AK inverse corresponds to the physical size lambda. So this is inside the horizon. This makes the time independent frequency, but in the upper side cases, super horizon size is the frequency becomes time independent. So in the sub-horizon case, the frequency the time independence and the physical size is extremely smaller compared to with the Hubble horizon size. So gravity box can be neglected. So this is almost a mean cosp matrix, so that we can use the formulation of the quantum mechanics. So we can expand this Hamiltonian in terms of the operators, and we should minimize this Hamiltonian to bind the vacuum. So equation motion is just a Hamiltonian form with the time independent frequency. This gives the plane wave, and if we insert, so we can bind the minimum Hamiltonian at the specific amplitude and the specific phase. So the solution of the this mode function. So again, this is just the change of the variable from the scalar perturbation u, and we lost that all the term as the operator version, and this is just a solution. But even though we can find the minimum of the Hamiltonian and the vacuum state at a specific time, but the Hamiltonian is over the time, and so the vacuum state is also about the time. So the vacuum becomes changes. This means that if the new operators that acts on the vacuum state, the particles are produced. And the connection between the two different operator or mode function or two different vacuum can be connected by the Bogoliubov transformation. This can be written by the linear to preserve the canonical conjugate relation. The coefficients of these Bogoliubov transformations should satisfy this condition. And the important thing is the vacuum state changes. So if we ask the number of operators by defining by the lattice operator, at the specific time, the number of operators yield at the zero expectation value, but after the some times going on, because the vacuum state changes, so the if we act on the number of operators and the expectation values of this becomes a non-zero, this means that the particles are produced. So the point is the gravitational background with expansion effect make the time-varying vacuum. This makes the gravitational particle production one important result. So in the remaining time, we can also obtain the solution for the sub-horizon and super-horizon regions as a limit. One thing mentioned that in the super-horizon region, U is just given by the proportion to the jet, and the R, curl R is U over the jet, so the scalar perturbation becomes a constant in the super-horizon. This is a limiting solution, and we can connect the solution. The general solution is given by the Bessel function, but usually it's used by the Hankel function to cover the limit solution smarting. So the point is still we just bind the scalar perturbation, and we use operators with the quantum mechanics version, and we find the solutions. In this space, epsilon and eta is equal to 0, and the Turing population is small, so that we can approximate this. And similar for the tensor, we consider only the scalars, but if we consider a tensor, there will be the polarization. So now we will turn to the power spectrum. Already the power spectrums can be obtained by the two-point correlation functions after the Fourier transformation. So this is the two-point correlation functions in the distance space, and by the Fourier transformation we can obtain the power spectrum. So this is the power spectrum of the scalar perturbations. The definition here. This corresponds to the momentum conservation, And the expectations is with respect to the vacuum, and the vacuum that changes over the time. And if we consider dimension, the delta function is m to the minus 3 because the delta function's integration over the space through the momentum space should be the 1. And the Scalar perturbation is also m to the minus 3 if we consider the actions. So from that, the path spectrum has a mass dimension of the minus 3. So to make the dimensionless path spectrum, we multiply the K3, and this is can be denoted as the curly P, or sometimes it can be written by the capital delta. And as ensemble parameterizations of this primordial scalar perturbation path spectrum can be written by the logarithm 1, amplitude, and the dependence of the k as a power law. So when n is equal to the 1, this is just a plot which is called the scale invariant power spectrum. And the NS is just called the tilt, or the spectral index. When the NS is rather than the 1, the power spectrums that tilt is the blue one, the small scale of the k. I mean the small scale of the distance and the large frequency. When the NS is smaller than the 1, this is large tilted. And the non-values of the NS is 0.96, quite slightly little from the blood. So this is NS, and from the CMB we can obtain the A are the amplitudes and the spectral index. The A are amplitude 10 to the minus 9, and if we consider roots of the AR, this gives the temperature anisotropic consistency with 10 to the minus 5 scale, and NS is 0.96. So the final one, the primordial power spectrum can be obtained by the following form as a solution. There is dependence of the slow parameter epsilon and etc. and k dependence. The primordial such a power spectrum so becomes constant. They can handle when the scalar is outside of the horizon. So we already discussed. And by multiplying the transfer function over the primordial power spectrum, the transfer functions includes the evolution at the radius and number. The dominant is a non-value. This includes the BBN or something. So we can obtain the power spectrums at the CMB approach. So similarly for the tensor perturbation, there is the polarization summation, dimensionless power spectrum. And we can define the R, the tensor to scalar ratio. There is a relation with epsilon and NHs. Also, for the tensor power spectrums, there is the scaling law with the spectral index. But the tensor perturbation can't detect yet. The tensor perturbation influences the B mode polarization of the CMB. The gradient modes correspond to the E mode, and the rotating curl modes correspond to the B modes, and the gravitational wave or tensor perturbation gives the B mode polarization of the CMB. This means the distorted space-time by the gravitational wave, and the upper bound of the R is known as 0.03. So here again, this is some specific in Plato model. You can impose an equal 60 board. Epsilon 1 gives the binary values already in Platon. Power spectrum. So from the power spectrum, amplitude to the 10 to the minus 9, this imposes the scale of the mass, and NS and R. So AS and NS can be obtained from the Scalar power spectrum, and R can be obtained by the tensor perturbation. But R is 0.1 in the such a power law, so this is excluded. But such a large build model, the build changes is the multiplication of the number of some Planck mass scale. This means that the build value is super Planckian, but the quantum gravity is unknown, so we use the effective build approaches but the build value is a super Planckian, but the scale cutoff is usually smaller than the sub Planckian. So the sub Planckian high dimensional sort of Pareto corrections that make the substructures, it make the potential shapes different. So the in the effective approach is the shape of the potential is not natural. So the super Planckian implantation model is not natural. Also, there is a supergravity potential as well as supersymmetry motivation. Now, in the remaining part, the final topic is the implantational evolution of the quantum state. But I will skip the older things in here. There's inverted harmonic oscillators. The potential shapes are different. We can draw the phase diagram from the Hamiltonian. And the important thing is in here is if we consider the 45 degree rotations of the phase space Q and the P, the phase space distributions are squeezing. The circles becomes the oval here, and also we can written this as the quantum mechanics version, and also that there is operator versions, and the time evolution operator becomes a squeezing operator. And we can apply it in the cosmological evolution for the Scalar and so on. Operators version Fourier transformation and lattice operator. And in this case, now the operator becomes a time dependent due to the gravity effect. And this gives a time dependence of the solution. And such as squeezing operators makes the new particle due to the time dependent one. So today we discuss too many things for this implantation one. But I want to say that there are some take-home methods. The first one, why the implantations is necessary. This comes from the horizon problem. The physical size at the CMB time is smaller than the horizon size, because the horizon size is increased more faster. So we need the implantation, and the afterlight expansions can resolve this. And how much implantation necessary? By evaluating the physical size and horizon size, the n equal to 60 e-volts is necessary, and by introducing the scalar fields and the specific potential, we can determine the order quantity. And the implantation field fluctuation gives the primordial perturbation. The scalar curvature perturbation currently R is the invariant quantity, and we can obtain the equation of the motion depth. And as answers, the power spectrum supporter such as scalar curvature perturbation R has the power law. For the scalar one, the amplitude is AR, and the spectral index NS is the important one, and it is calculated by the lower parameters. And for the tensor perturbation, the tensor to scalarity of R is important. And NS is measures, and R has a upper bound, so that we can test the specific potential shapes of the implantation. And the one thing so that we can write all the thing as a brightest version, and because the vacuum stays the time dependent due to the expansion effect, and this can make the gravitational particle productions because the vacuum state the changes. Yeah.